All right, everyone, another week, another module. Let's go ahead and dive into chapter 3, and we'll be starting out at quadratic functions. Now, really what we're doing here is we're going to kind of revisit function transformations, but also see kind of just in general what quadratics do and how they could be transformed and written in various methods. So, without further ado, let's go ahead and get started. First thing we're going to say about quadratics is they have something called a vertex, and that vertex is, let's say by definition, um, the min or max of the function, I'll just say of function. And just remember that quadratics could look something like this. So, right, that would be your vertex. From there, there's of course, or maybe not of course, but there's also what we call an axis of symmetry. And that's simply going to be x equals, we're going to refer to it as h. And also for this vertex, we're going to refer to it as hk. All right. So in other words, if you notice, the axis of symmetry is x equals the x value of the vertex. And why? Well, here's your axis of symmetry. And you can see what we mean by that. There's literally a line of symmetry going right through that min or max point. All right, so there we go. There's your axis of symmetry. Now every, let's say this, every quadratic has a y-intercept. And we know how to get that. We simply let x equal 0 and solve. And then the harder one is the x-intercepts. Now, not every quadratic actually has x-intercepts. In fact, this first quadratic I just drew never actually crosses the x-axis, and well, there's stuff we could do about that, but we're not going to worry about that in this section. But the x-intercepts would be either found by factoring or using the, we learned this before, quadratic formula. Okay. So finally then, what do we do with this information? Or how do we assemble this information? Well, there's two more things we need to look at, and that's forms of quadratics. Now, let's start off with two of them because factoring is the third form, but factoring is usually something you get to from one of the other two forms. And so let's talk about it. Well, there's vertex form, and vertex form looks like this. And this should look very familiar to you because this should remind you of when we went through function transformations. We talked about moving left or right, and we talked about moving up or down and vertical stretches. All of that is right here. So essentially, if you have a quadratic and vertex form, you're ready to classify function transformations directly from this equation. That's why it's beneficial. And why do we call it vertex form? Well, because remember, we call the vertex h comma k, and look at what's right here. H is on the inside, adding or subtracting with x, the thing that makes the function its name, as we call it, and then k is adding or subtracting afterwards. All right, now what's the other one? The other one is, I guess, what we would just call standard form. Oops, form. And standard form looks like this. And you've actually seen this as well when we went over the quadratic formula. Now, what's super important that you realize is that this A here and this A here aren't just used, what's the word? Just randomly. They actually mean something significant, or rather, they are the same thing. So, in other words, to be a little bit more descriptive with our function transformations, this value of A is telling you about potential vertical stretches or compressions, like we talked about. It's also, if A was negative, telling us if there's been a flip. Now, if there's a flip, as you're in this section, the way we'll describe that is, does this graph open upward or does it open downward? So if this A ends up being negative, we now know that this graph would flip downward. Okay, With all that being said, let's dive in. And also, we said domain and range, but don't worry, we'll get there. So, state the vertex, axis of symmetry, domain and range. For this first one, I hope this one is super easy because it's our first example and it's already in vertex form and it pretty much almost matches. So I know what my vertex is. My vertex, now careful, watch this, is +2, -3. This again, like I said, is a callback to when we went over function transformations and what's on the inside of the thing that gives it its name gets reversed. If it's -2, then it's actually right 2. But if it's plus or minus 3 at the end, it is plus or minus 3 stated as it is in the vertex, or in the function transformation. So this is down 3, which matches, and this is right 2 because it flipped. All right, great. We have our vertex. Now we need the axis of symmetry. That should be super easy. It's x equals the coordinate of my vertex. Done. Now what's the domain? Well, this goes back to also what we talked about before. Your domain is simply going to be -infinity to +infinity because there's no fractions and there are no square roots, so there's no issues. We can always plug anything into here and get an answer out. Now, finally then, the question is, what would the range be? Now, we don't have to draw this graph to know the range. If we think about this picture, the fact that A is the number out front, not the problem number, but the number out front of here is +1, so we know that this quadratic opens upward, and we now know where the vertex is, which means we found the lowest point. So my range, catch this, is going to be bracket that k value, because it's either the lowest or the highest, and then to infinity because it opens upward. So that was pretty easy. And now we're going to fly through the rest of these. Well, I guess the next one at least, because the third one is going to be a little bit different. So how do I find the vertex for this one? Well, just like before, it's going to be +3 and +7. Change the sign of what I see inside here, copy it as is. I now know that my axis of symmetry is x equals 3 because it's the value from my vertex. I know for a fact my domain and range is -infinity to infinity because it always will be with quadratics. And I know, ooh, careful, because this graph opens downward. It was vertically stretched also, but we don't need to worry about that now. This graph now opens downward, so its range is, watch this, -infinity, because it's going downwards. It looks like that. And the lowest it will go is down forever, but the highest it will go is the +7 bracket. So, in other words, whatever this graph looks like, just to draw shorthand, I guess it went right 3 up 7. It looks like that. Right? There's a really, really quick freehand, and not to scale, but I think you get the idea. And hopefully that shows you the range, that it is going down forever. Again, why is it opening down? Because there's a negative in front of the thing that gives the function its name. All right, finally, we have a standard form example, and there's one last thing we need to do, is we need to find another way of finding the vertex. So we'll write that here now. Um, why not? I'll be a fancy mathematician. So, when you have a standard form, what you do is you take a look at those numbers, the one in front of the x squared, the one in front of the x and the c. To find the vertex, the x coordinate of your vertex will end up being -b divided by 2a. Whatever that ends up being, plug it in and solve, and you just found the y value of the vertex. So this one's going to be a little bit different and take a little bit longer to get there, but let's try that out. So -b would be -42 over 2 times a. And you know what? I'm now realizing that that is going to not work out nicely because I chose 42. I meant to choose a different number. So what we're going to do is we're just going to make this instead, what are we going to make it? I think I meant it to be 48. So sorry about that, but let's go ahead and make that 48. And maybe I'll correct that on the PDF. So anyways, 48. Great, because now that works out nicely. We don't want to deal with fractions yet. So negative 48 over 8 is negative 6. Great, I just found the x-coordinate of my vertex. So now the y-coordinate is going to be 4 times negative 6 squared plus 48 times negative 6, and then minus 7. And I'm going to pause this and work it out myself, but you have a calculator, trust it, try it, and see if we get the same answer that I'll show you in a second. Okay, that one was a little crazier than I thought, but no worries. At least we're not graphing this, but it turns out when you evaluate this, that'll be 36 times 4, which is 100, I think 40 something, 44. And then we multiply that by 48 times negative 6, subtract the 7. Long story short, at the end of the day, you should get negative 151. But remember that this is going to be, whatever this first thing was, should have been positive something, because that negative 6 got squared and became positive. Anyways, I now know my vertex. It is negative 6 comma negative 151. And just fun fact, because I've now found this out, there's a way to rewrite this in vertex form. This is not what the question's asking, but let's do it anyways. That means I now know that this could just as easily be written as, careful, watch this. How do I know that? Great question, because remember, the a out front is the same a in any form, so since there was a 4x squared, I know that the number out front of my vertex form is 4. I just found my vertex out of standard form by doing negative b over 2a and plugging in. And so now I know what the h value is and the k value is, and remember the h value flips after you find it. So that was pretty cool. We just learned how to go from standard form into vertex form. We just had to calculate the vertex form, or the vertex, paste it in, so to speak, and then just copy the value of a. Interesting. Now again, that wasn't what this question asked, I just wanted to point that out to you, that you can make that leap. From there, the axis of symmetry would be x equals negative 6. We already know what the domain is. It's negative infinity to infinity. And then finally, the range, sorry, this one's running out of space here, there was so much to do. The range is going to be, well, let's think about it. This is a positive 4, so this graph's opening up, so that means that this value, negative 151, because it's opening up, is my minimum, so my range is from negative 151 to infinity. Awesome. So when it's in standard form, again, remember that you're going to need to use negative b over 2a, evaluate that, and go. All right, now we've got more questions here, where now we want to state the vertex, axis of symmetry, and x-intercepts. Well, let's go in order, and let's still, again, practice finding the vertex out of standard form. The x-coordinate would be negative b, which is now positive 6, over 2 times a, and that ends up being 3. All right, now I need to plug 3 in. Once again, I'm going to do that. I'm going to write it, but then I'm just going to show you the answer for sake of time. But you should pause, think, take your calculator, review it later, put a star to remind yourself to evaluate and get the same answer. But that's a positive 9, that's a negative 18, and then plus 5. Let's see here. Well, 9 minus 18 is negative 9. Negative 9 plus 5 should be negative 4. All right, so I now have my vertex. It is 3 comma negative 4. The axis of symmetry, again, we know what that is. It's going to be x equals 3. It is a, again, vertical line that crosses through the x-axis at 3. Now, finally, I want to find the x-intercepts this time. Now, the x-intercepts, we said, would be done by using factoring or the quadratic formula. And so the question is, can this be factored? And the answer is yes. There are factors of 5 that add to 6. And so that means, and they are 1 and 5, there's a way to write this in factored form. Now the question is, what signs do these both need to be? Well, if they're going to multiply to be positive 5, but combine to make a negative 6, each of these have to be negative. Now watch this idea. I now know what my x-intercepts are. They're what make either of these equal 0. And if I solve that, or if you kind of think about it like vertex form, what I'm going to get here is I'm going to get x equals 1 and x equals 5. I plug 1 in, or the sign flips, to make that 0. I plug 5 in, or again, the sign flips, to make that 0. Those are my x-intercepts. Just watch carefully the way your homework wants it. They would like you to write it as points, as 1 comma 0, because it is a point, and then 5 comma 0, because that's what it means to be an x-intercept. Your y-coordinate is 0. So great, we found the vertex, we found the axis of symmetry, we found the x-intercepts, we're done. We'll look at the other two. They'll be a little bit interesting. All right, for this next one, this one's going to be a little easier because we're back to vertex form. So the vertex is really easy to find. There it is. Flip the sign from the inside of the parentheses. Again, that should remind you what we did in the factoring. And just copy the y-coordinate as is. The axis of symmetry, again, would be x equals -3. So that's the easy one. And then here's what's going to be a little tricky, but we're going to make our lives easy. We want to find the x-intercepts of this. Now, there's two things you could do. You could either, let's see here, distribute this all out and get it into standard form and factor. Or in some cases, you might be able to get away with looking at the graph. Now we'll talk about this later, and it is kind of special that this one works out. But let's think about what I'm going to start calling quadratic motion. So if I had an axis here, and I were to go, let's see here, left 3, 1, 2, 3, and down 4, there'd be my vertex. Now, the number out front of here is 1, which means it hasn't been flipped to open downward, and it hasn't been vertically stretched, and we've talked about this a little bit, but quadratics, remember, what they do is from the vertex, they would move right 1 and go up 1, and they would go left 1 and go up 1, because after all, there is an axis of symmetry. Now from there, if they go right 2, because this is squaring, if I go right 2, I would end up going up 4, and look at where I would end up, back on the x-axis. And so I just found my x-intercepts by knowing the shape of this graph and getting lucky that this graph ended up crossing at 2 points. And I know that I did get lucky, but let's go ahead and write those 2 points down. They are, let's see here, -1, 0 is the first one, I guess. And the second one would be, well, let's see here. If this is a symmetry line and this is -3 and I went 2 over to -1, catch that again. If this is the symmetry line at x equals -3 and I went right 2 to get to -1, then from -3 I should be able to go left 2, which would put me at -5. And those would be my x-intercepts. Um, to say it the other way, or to do it the other way by factoring, what you would do is you would FOIL this out, and careful, when you FOIL that out, what you would get is x squared plus 6x plus 9, but then there was a -4, so it was +5, which is actually eerily similar to this example. It's just that sign switched, and maybe you could see that. Again, you could take this and factor it out afterwards, but I'm just trying to say that's really your only other option. If you don't get the graph and it doesn't cross nicely, you would need to FOIL this out and then try to factor this. All right, on to the third. For sake of time for the third, I'm not even going to bother writing down. Well, never mind, I will. But the vertex is going to end up being, let's see here, -7, comma, whatever I get when I plug 7 in. Now that I am going to work out quickly. And that's what you get when you plug in -7 into this. You should get -43. So there's our vertex. I'm not going to bother writing down the axis of symmetry because here's the big thing we need to wrap this video up with, but it will take a little few minutes or so. We need to realize that, hey, there are no factors of 6 that add to 14. So what are we going to do? Well, unfortunately, I gave you the answer a while ago. You either do factoring, or if you know factoring won't work because there were no factors of 6 that add to 14, we're going to need to use the quadratic formula. So to close out this video and almost be done with 3.1, let's review the quadratic formula because I know we looked at it earlier in earlier modules, and I know you probably thought to yourself, well, he hasn't talked about it in a while, but here it is. It's back for us. So the quadratic formula goes negative b plus or minus the square root of b squared minus 4 times a, which is that number in front, times c, which is the number at the end again, all over 2 times a. So these will be the x-coordinates of my x-intercepts. All right, one thing I want to point out, just in case this is, or sorry, I wrote a instead of what a is, which is 1. One thing I want to point out is, hey, look, negative 14 divided by 2, negative b over 2a is in your quadratic formula if you didn't realize that. So there's negative 7 at some level, but there's this other thing, which by the way, it does have a name. We technically call this the um, discriminant, or rather we call the interior of that square root the discriminant. And maybe we'll get to that later, but I just wanted to point that out. So there's your x-coordinate of the vertex, and you move a certain amount to the right and a certain amount left, and that amount is this thing, the discriminant. And that should make sense because look, it's symmetrical. Where you cross the axis is symmetrical. So in other words, I know, well, never mind, let's just do it. But, well, it's worth saying, we got so close. I know that essentially, in this quadratic formula for this question, this plus or minus square root ended up being worth 2 because after all, from my vertex, I ended up being able to go right 2 and left 2. That's what this is saying, in other words. How far did you scoot over from your line of symmetry? Anyways, let's work out the quadratic formula and be done with this video. So, to work that out, we've said our next goal is get one number in the square root. Let me do that. All right, when you work that out, you should end up with 172. That's 196 minus 24. Now from there, we're so close to being done. Now you might think, let's divide everything by 2. Do not do that yet because the square root is covering the 172. We can't divide it. And we've talked about this before. Again, it's been a while, but there is actually in 172 a perfect square hiding inside. There is a 4 inside of 172. Now, how did I know that? Well, because I said to myself, any square root needs to be checked for square roots, and thankfully the first, you know, one is a perfect square, but we don't care about one. So I tried the next perfect square, which is 4, and it happened to work. Now look what I got left over with, 43. 43 doesn't break down any further, so I now know I've found my largest perfect square and the leftovers. So take a look, I can now write it like that. So this is now 2 root 43. And let's continue on to the next line. The next line would be negative 14. Here we go. Plus or minus 2 root 43 all over 2. This is finally where I can divide because take a look at the 14 on the outside and the 2 on the outside and the 2 on the outside. Those can all reduce, and so I end up with negative 7 plus or minus root 43. And so essentially, I'm going to lazily write it like this. These are your x-intercepts. This is the x-coordinate, the one where it's positive and the one where it's negative. You'll need to write both. I'm just lazily writing it as plus minus for myself. And then comma 0, because after all, these are points. That's what the x-intercepts are. So there was a quick revisit of the quadratic formula. Write it in, get one number in the square root, break the square root down if you can, and then reduce if you can. Very last thing to say is it is a total math coincidence that this negative 43 of the vertex ended up being in the square root. That does not always happen. In fact, it very rarely happens, but hey, so I just wanted to point that out. It is a coincidence and don't expect to see that all the time. But that's all for now. We have a little bit of 3.1 to wrap up and then we'll move on. So I'll see you in the next video.